Hi, everyone. Welcome to the keynote lecture of the second week of the Nuclear Engineering Summer School. Today, we have on Eric Hall, our guest speaker. It is my honor to introduce him. He's a PhD student with the University of Michigan under the supervision of Professor Zhong He, and has focused his PhD work on thallium bromide semiconductor detectors. He's close to his defense, and today he will be covering his detector of choice, as well as additional alternative semiconductor detectors. Eric, please take it away.
Thank you, Flynn. Thanks for the introduction, and thanks for inviting me to give this talk. All right, I'll share my screen now. Okay, so is the slideshow coming up well?
Yeah, looks good, Eric.
Okay, great. All right, so I'll talk about today, as Flynn said, I'm talking about thallium bromide and other alternative semiconductor materials. So I'll go over a quick comparison of scintillators and semiconductors. Then I'll go over material comparison of a few semiconductors. The bulk of the presentation will be about thallium bromide, which is what my research has been in primarily. And then I got a couple slides at the end talking about mercuric iodide and perovskites. Okay, so comparing scintillators to semiconductors, they each have their advantages. So it depends on what application you want to use them for, which will determine what material you want to use for that detection. So for things like event time, if you're looking at the response time of scintillators, it's measured in like nanoseconds, or some of them are even measured in picoseconds, whereas semiconductors are measured in like a few microseconds. To thallium bromide, it's like tens of microseconds. So if you need something where the events are happening very quickly, scintillators are where you're going to want to go with. The next criteria is collection method. So scintillators are what's described as like they have an indirect mechanism. So like the gamma ray comes into the scintillator, scintillates photons. Those photons are collected by a photocathode or a SiPM, converted to electrons, and those electrons are multiplied down the PMT and then measured. Whereas with semiconductors, the gamma ray comes into the semiconductor, interacts, creates the electron cloud, and then the movement of that electron cloud is measured. So because it's direct, it introduces fewer methods for loss of signal. So the theoretical limit, or the theoretical best resolution of scintillators is like 2%, I think, 2 to 3%, whereas the theoretical best limit for a semiconductor is like 0.2% resolution. So it's much better there. As far as costs, scintillators, I know this can vary very widely across all materials for both scintillators and semiconductors, but in general, scintillators typically have a lower cost for materials and production. And then for system size, again, this also varies across materials for both scintillators and semiconductors, but generally, for a given application, you can use a smaller semiconductor than you would use for a scintillator. So assuming other like electronics attached to those materials are pretty similar, you can accomplish the same thing with a smaller semiconductor than you would with a scintillator. All right, so now I'll go over a material comparison to kind of like give a frame of reference for what I'm going to be talking about today. So let's see. So the first material here is high purity germanium. Okay, yeah, there it is, high purity germanium. So high purity germanium is like the standard that we all learn on for radiation detection. It's used in most labs that I know of for gamma ray detection. CZT was pioneered by our group here, and it's very, very well commercialized by Professor He's company, H3D. And then my research today since I've been a PhD student, is in thallium bromide. So I'll compare a few characteristics of each of these materials. The Z, or the atomic number, is lower lower for high purity germanium, and then it gets better and better with each of these materials. So the effective Z of thallium bromide is something around like 68 to 70, but that makes it, the higher Z makes it better for interacting with gamma rays. Same thing for density. So with each of these materials has an increasing density. So thallium bromide has the advantage here. Again, makes it better for interacting with gamma rays. The band gap. This is a characteristic that describes the energy required for an electron to move from the valence band to the conduction band. So anything, a material with like no band gap is essentially a conductor. Whereas like a material with over 5 eV of a band gap is basically an insulator. So semiconductors are right in that gap of 0 to like 5 eV. Now, if you know anything about high purity germanium, you know that it needs to be cryogenically cooled down to like 77 Kelvin in order to be useful as a radiation detector. And that's because it has a relatively small band gap of 0.72 eV. Because at room temperature, electrons can be thermally excited just from like the ambient temperature from the valence band to the conduction band. So that will mask any radiation signals that you'll see from this material. So that's where like these what we call wide band gap semiconductors work for what we would say is room temperature detection. So just this increase from 0.72 to 1.64, this enables CZT to be useful in detecting the movement of electrons from radiation interactions at room temperature, which is about 300 Kelvin. So thallium bromide is one step better than that, increasing that band gap from 1.6 to 2.7. So whereas CZT struggles at temperatures above 40 degrees Celsius, thallium bromide theoretically should work fine at those temperatures. But we're still researching that. So next characteristic is ionization energy. This is the energy required to create, when that gamma ray interacts with the material, to create that electron hole pair. Now the advantage here is still high purity germanium. So it's only takes about 3 eV to create an electron hole pair, whereas with these other materials it takes 5 to 6.5 eV to create an electron hole pair. But even though it's not quite as good as germanium, it's still pretty good. It's not like for like a gas detector, it was just like 30 eV to create an electron ion pair. So still usable for spectroscopy. And then some other factors here are the mobility of the electrons and the holes in the material. So with germanium, the mobility is relatively quick, which helps if you're dealing with like a higher flux source. But these mobilities are fairly similar to each other, which means you're recording the signal of the movement of both the holes and the electrons. Whereas with other materials like CZT and thallium bromide, there's a significant difference between the mobility of the electrons versus the mobility of the holes. So these materials, we kind of call them single polarity charge sensing. So on the time scale that we're looking at for the movement of an electron, the holes have like barely moved at all. So we essentially consider them to not move. So when we're looking at our signals, we're basically only looking at the movement of the electrons. So overall, semiconductors like thallium bromide has a better efficiency due to the effective atomic number and the density. As far as crystal growth, the simpler cubic structure of just thallium and bromide versus CZT means that CZT requires like a vertical Bridgman furnace operated over 1,000 degrees Celsius, whereas thallium bromide can be grown in a horizontal coarse ampoule with temperatures like below 500 degrees Celsius. So that should make it cheaper and simpler to make. So you already touched on the band gap. So overall, if we can get thallium bromide to work as a room temperature semiconductor, it should be cheaper and easier to distribute detectors using thallium bromide versus CZT or high purity germanium.
Eric, quick question
Sure.
from Siddharth Gupta. Is there any relation between band gap and ionization energy?
band gap and ionization energy. I've never thought about that before, but I would say probably. I'm sorry, I can't give you a better answer than that.
Fair enough. And then there was an earlier question. Yes, I've got your question, Abhishek. The direct collection method is slower, but why? Why would it be slower for the direct method rather?
Okay, I would say that's because of the this. Ooh, see where my mouse go. Okay, that's because of the mobility here. So we're in semiconductors, we're having to work with the mobility of like the electrons inside the medium of the detector. Whereas with like a scintillator and a PMT, you're depending on photons that are moving at the speed of light inside that material, as well as the electrons moving through a vacuum of the PMT. So those both should be faster than like an electron moving through a dense material like thallium bromide or CZT.
Thanks, Eric. That's it for questions.
Okay, cool. Okay, so for signal collection. So in our group here, we work with almost entirely pixelated semiconductors. So on the left here, you see an example of a thallium bromide crystal. We have a pixelated anode on top here, and then the bulk of the crystal about 1 centimeter thick, and then a planar anode here on the bottom. So if you look at the pixelated anode, you see a 3x3 pixel array, and then all these other pixels that were created during the electrode fabrication or not bonded, wired together as a guard ring to reduce any leakage current that might be going over the surface and material on the outside. So the way we do our signal collection is based on what we call the Shockley-Ramo theorem, which is an example is depicted here. So for a pixelated sample, the pixelated or a pixel weighting potential is shown by this curve here, whereas the planar cathode is shown by the weighting potential here. So when you have a gamma ray interact in the crystal, create the electron cloud, and then start traveling towards the pixel, it'll create this signal waveform here. So the signal that it creates is based on the weighting potential. So if you imagine this being like this being the cathode side and this being the anode side, if a event happens maybe like midway in the bulk of the crystal, as it's traveling towards the anode, it will travel through this potential and create this signal here. And then that same electron movement will also create a signal from the planar cathode based on this portion of the cathode weighting potential here. So that you can see that an example of this here in the bottom right of an event that happened like in the middle bulk of the crystal creates this pixel waveform and this cathode waveform. So from these waveforms, this is where we start getting all of our information from. The amplitude of this pixel waveform is where we get the energy of the event. Now, if we compare that to the amplitude here of like the cathode waveform, we can use that as sort of a proportional representation of the depth of the interaction of the crystal. And then another method that we have is if we consider this point of inflection here to be the start of the event, and then this point of inflection here to be the end of the event, we can use that drift timing to also describe the depth. So like an event that happens close to the planar cathode will have very short drift time, whereas an event closer to the, sorry, I got it backwards. An event closer to the pixelated anode will have a very short drift time, and an event close to the planar cathode will have a very long drift time because an electron cloud will have to drift through the entire bulk of the crystal. So looking at first, if we just consider just the amplitude of the pixel waveform here, I go to the next slide. Using the amplitude of all those events from the pixel waveform, we create a raw spectrum here. So this is a raw spectrum for cesium-137. If you know anything about cesium-137, we have a photo peak here at 662 keV. This axis here is just using the ADC units from our readout electronics. But we have an escape peak here for thallium. It has a about 80 keV escape X-ray. So if the event happens close enough to the outside of the crystal, that X-ray will escape and we'll lose that energy. And instead of an event being recorded in the photo peak, we'll record a smaller, what we call an escape peak. You see the Compton continuum here and a backscatter peak here. So if you take this raw spectrum and you flip it on its side, you can look here for that 3x3 pixel array. Each the x-axis is the energy of the event, and then the y-axis on each pixel is here it's the drift duration of the event, but it's essentially what we call the depth of interaction with the event. So if you take the events and you look at their energy as well as their drift duration, you can kind of look at these raw spectra in depth in each depth slice. So where you see the photo peak here, as an example for this pixel, this is like the photo peak at each depth for that pixel. So where we get what we call a depth correction is if we find the centroid of the photo peak at each of these depths, and then we recalibrate all the energies to that photo peak centroid, we can create a depth corrected spectrum here. So instead of a raw resolution of 10.5%, our depth corrected resolution improves to 3.1% at 662 keV. So that's important if like in this crystal, there's probably a little bit of trapping, which is one factor that will change the photo peak energy recorded at each depth. But there's also maybe a material non-uniformity that causes a different gain in each pixel, or your readout electronics. We have a separate preamplifier attached to each of these pixels, which I'll go into in a later slide. And each of those preamplifiers will have some slightly different manufactured gain. So that's another thing that we need to correct for when we do depth correction. All right, so beyond that, I'll go into reading out thallium bromide with discrete preamplifiers. So when we read out thallium bromide with discrete preamplifiers, essentially, you can see in this crystal here, from each of these pixels, we have a wire, a very thin wire going to each of these pins. The pins plug into a board. The board has the preamplifiers mounted to it. And then so the signal is read out through the preamplifier and then output from the preamplifier to we have a digitizer, a computer with installed digitizers in it, and it digitizes all those waveform signals so that we can process them later. So a lot of those settings are fixed and we can't change them. But let's see what we got here. So in this slide, I have an example of this one crystal that we have from Tohoku University. It's a thallium bromide crystal, and then the electrodes themselves are made out of thallium metal. So one of the problems that we're trying to solve here is that if the electrodes are chemically reacting with the bulk of the crystal, if they're reacting with thallium, then it's just thallium switching with thallium, so it should reduce that problem. So this crystal itself, or also with thallium, it's reacted with the air. So this was taken before it was entirely encapsulated. So yeah, and this is the only crystal, one of two crystals like this that we've received in our lab. Most of our crystals have a different composition. But you can see here with a raw spectrum, really poor photo peak resolution for cesium. But using our depth correction methods, we're able to get a much improved resolution of about 2.4% at 662 keV. Supporting research done by that university, we also found that when we look at this crystal, pretty clear photo peak in all the pixels at the beginning of operation. But then after about 35 days of operation, the events, you can see the photo peak becomes blurry in a lot of these pixels. So from that, we can see that there's a photo peak still at all depths, but because the energy that we're recording from them is less precise, we think something's going on with the electrodes. So if we switch the bias, we introduce a positive bias for 35 days. That seems to have corrected the problem, because when we apply a negative bias again and do another measurement, the photo peaks are clear again. So this supports the work that Professor Hitomi has done at Tohoku University. So beyond that, almost all of the other crystals that we've tested in our group, made by radiation monitoring devices in Boston, they use some electrode material other than thallium. So they can be composed of like platinum or gold, chromium, palladium, or these are the four most common, but I'm sure they have other materials that they've used as well. And then they tried different chemical etching. So after the crystal is grown and then cut, some chemical etching needs to be done to smooth out the surfaces before the electrode material is applied. So they've used different methods there, whether it's hydrochloric acid, methyl bromine, or even just distilled water. They've tried each of those. And the best result we've gotten from these smaller crystals, you can see pictured here, it achieved a 2.6% overall resolution at 662 keV. And the best pixel was the one in the middle here at about 1.9%. So after we did all this testing with these smaller samples, we decided to move on to testing thallium bromide with an application-specific integrated circuit. So we have one in our group that we've developed in conjunction with Ideas of Oslo, Norway. And here's a picture of it here. So this is this helps shrink down our readout electronics, and in the process of shrinking it down, also reduces all the trace lengths and helps us reduce electronic noise introduced in the measurement. So instead of long trace wires in PCBs and cables themselves, so go into like preamplifiers and digitizers and like separate components, we have it all contained here in this ASIC. And I don't have anything for size reference, but it's only barely larger than a crystal. So it's maybe 25 by 25 millimeters wide, and then maybe 5 millimeters thick. So you can see all these three 42-pin connectors allow us to have 130 channels. So 128 we can dedicate to pixels, 2 for the planar contacts. We can change the gain. We have 160 capacitors for each channel that we can use as a pipeline to sample waveforms as they come in. It was designed to operate from as fast as 80 megahertz to as slow as 1.25 megahertz. So the higher ranges are used for the faster materials like CZT, and then we use the lower end, the slower sampling rates for slower materials like thallium bromide. And then as far as the circuit architecture, there's a shaper to determine the trigger for each channel, as well as the sampling pipeline. So a problem that we found when we were operating thallium bromide on the Ideas ASIC is that it seems like a lot of the settings that when it was designed to be flexible, to be used with a lot of different semiconductor materials. But this one factor was the trigger shaper seems like it's not less than ideal for use with slower materials like thallium bromide. So the company quoted it as a 500 nanosecond trigger shaper. We found it was slightly adjustable between 400 to 600 nanoseconds, but still it's still really fast for thallium bromide. And we found that because it was so fast, it was rejecting some events when conducting measurements of thallium bromide. So if on the left here I have a video, it's all the pixels from a 9x9 pixel array, but let's just focus on this one pixel here. You can't, if you look at it, there's no photo peak really that you can see, but as we adjust the trigger shaper, you can see the photo peak become much more obvious with different settings. So this enabled us to record more bulk events and actually do our depth correction technique on this crystal, or on thallium bromide in general. Okay, so from there, in our project, we've also partnered with H3D. They've devoted a number of these S series to our project. This is a commercial line of systems that they have, and the enclosure and all the electronics and all the software, it's all optimized for CZT, but we put thallium bromide in it to see if it'll work. And it works adequately. Like you can see here, this is our best system right now, the S200X Allegan. It has two 11 by 11 pixel arrays in it. They're both 10 millimeters thick with a 1.72 millimeter pitch. And if you look at the depth corrected spectra here, pretty much all the pixels are providing a pretty good cesium spectrum. I mean, you got a couple of pixels here, like here and here, that aren't operating well, but in general, it's working pretty well. And we're able to get like 2.2% resolution at 662 keV out of one crystal and 3.5% out of another. So combined, we're getting a 2.5% resolution. We're getting pretty good efficiency in that we're using two very large crystals. So a problem that we've been investigating is, if you remember back, we're looking for like a photo peak across all depths of the crystal. But we noticed with these samples that if you look here, like in this pixel or in this pixel, you'll see it looks like there's two photo peaks right next to each other, and it's happening to all these pixels in this crystal. And then at the same time, when we take these crystals out of our readout system, we're seeing like this pixel pattern develop on the cathode. So if our photo peak is like, if the events are changing, that's making our photo peak wider and degrading our resolution.
Eric, quick question.
Sure.
I was seeing on the picture of your detector there that it seems like maybe there's a hairline crack in the detector. Is that true?
No, that's actually a wire.
Okay, good.
This black spot is carbon paste.
Okay.
So the crystal manufacturer uses a slightly different method to read out the crystal, so they left this wire attached to the crystal, whereas we use like a conductive foam. So I was just pressing it down against the cathode, and since the wire was also conductive, I was not concerned that it was there.
Got it. Thanks.
But yeah, short answer is it's a wire. It's not a crack. All right, so if I go to this video, now this is 6 frames. There's only 6 frames in this video, but it's each day of a measurement in this crystal. I'm taking events from a certain energy in a specific pixel, and I've taken only events from a certain depth of the crystal. So I'm looking out of the entire crystal, I'm only looking at events from like one certain little like area of volume inside the crystal. But if you look at right now, this is the first day, and you can see the events are generally pretty consistent. And this is what we're looking for, and this will help us in our later processing. But then as the days go on, okay, yeah, as the days go on, you can see the tail starts to separate a little bit, and then by like the 4th day, you can see that there's essentially two main modes of operation where some events are still flat like they were on the first day, but then you see other events here have this rising tail. And this complicates our readout. So then when we looked at these events, we separated the events, and we looked at their position, the position of the event within the pixel based on whether they were events from this lower energy or this higher energy. So when we do that, we find that the events that don't really change are essentially coming from the center of the pixels, whereas the events that seem to have that rising tail, they all come from the edge of the pixels. And then when we look at it over time, we find that the center, if we separate events by their location and make an average of their waveform, if they're happening in the center the first day or the sixth day, it's essentially not changing. They're the same. However, the edge events on the sixth day have this rise. So we know that we've used these methods to pinpoint where the problem's coming from. Now we need to figure out what's causing this. But this is part of our ongoing research. One thing that we looked at is that all our samples previously used like a silver epoxy to bond the crystal to the carrier board. So, which was different from the smaller 3x3 pixel array samples that we were using previously, which used carbon paste. So we thought that might be causing the problem. One thing we've done is we've used a carbon nanotube epoxy to bond the crystal to the carrier board. And it seems to have worked so far. This crystal's operated for over 20 days with no changes. So yeah, this is another part of our ongoing research. And then another factor is I talked about earlier the trigger shaper, which was rejecting slow events in thallium bromide, was in the ASIC that was developed in a partnership between our group and Ideas. Well, we have an ASIC that we developed entirely in our group. We call the H3DD-UM ASIC, and it's gone through a few iterations. Right now we're on version 4. And essentially it's a very similar footprint, but different electronics outside of that. This is a dummy 11 by 11 pixel array that we've mounted on it just for size. But because we developed it entirely within our group, it has a lower cost than the Ideas ASIC. But it's also been designed with slower sampling rates and then a much larger sampling window to help with slower samples like thallium bromide. And then the trigger shaper is also much more tunable over a wider range. So it helps us collect more events and stop the event rejection that is happening with the Ideas ASIC. Okay, so beyond that, I have some other outside research I'm presenting here. So in our group, we're looking at thallium bromide as far as the movement of the electrons, but you can also use it to detect Cherenkov. So in this example here, we have a thallium bromide crystal with strip electrodes and a planar electrode, but it also has a PSI-PM attached to one side. So if you look in this example, we have if there's a sodium-22 source, we can do time of flight between this scintillator and then the Cherenkov in the thallium bromide. So the Cherenkov can be detected with a time resolution of about 330 picoseconds. So that's pretty comparable to what a scintillator is able to achieve. So this enables time of flight in a semiconductor while also still having the energy and spatial resolution of the semiconductor. And then some later work by this group at UC Davis also looked at pixelated anodes instead of the strip anodes as you see here, and then other materials like thallium chloride. Okay, so another material is mercuric iodide, which hasn't been researched recently, but our group was working with them while they were available. Let's see, I think in the early 2000s, so like 1998 to about 2006. See mercuric iodide, you can see a crystal here, very high effective Z, very good density, comparable to the other materials that I talked about earlier, very comparable band gap, and then the ionization, very comparable ionization energy. Again, comparable mobility. One of the downsides of mercuric iodide is that it sublimates at room temperature. So if it's left open, it'll just evaporate into the air. But so it has to be entirely encapsulated. We still have some samples here in our lab. I don't think anyone's tested that since I've been a student here, but they're here if we wanted to. I think the main problem was that there was only one manufacturer, Constellation Technology Group, I think, and they went out of business in the early 2000s. So a lot of research in this area has stopped. But this material held promise while it was available. And then the last material I have to go over today is perovskites. This is one of our hopeful areas of hopeful research for the future. So perovskite is anything with material formula of like ABX3. So examples would be like two cations, one anion. So like cesium lead bromide, or methyl ammonium lead chloride, or formamidinium lead iodide. We've gotten a few different samples here, or we've received a few different samples here in our group, but the majority of the crystals that we test are all cesium lead bromide. So again, has a very high effective Z, very good band gap of about 2.3 eV. It's found to be stable up to 70 degrees Celsius, which is really good. Most customers are looking for something that can operate up to like 60 degrees Celsius. So this could fit the bill. And then research done by another member of our group, Dr. Matthew Petrick here, showed that with this pixelated sample from Northwestern University, he was able to depth correct and get a resolution of 1.6% at 662 keV. So yeah, there's a few different manufacturers of this crystal, of this material, that we've gotten, mainly Northwestern and UNC Chapel Hill, but other places like I think Fisk University has sent us a few samples. Yeah, anyone that can make a detector out of perovskite, we're happy to test. And then another factor is the growth of this material. So like thallium bromide can be made cheaper than CZT, but perovskite can also be made in a furnace, like vertical bridgman furnace, or but it can also be made with a solution grown, because it's like liquid soluble. So that really doesn't require a high temperature at all. It just needs the right chemicals and the right and the right temperature just to let it sit, and the crystals will form themselves. So this potentially could be much cheaper and easier than other materials that are currently used. All right. So in summary, semiconductor strength are in very good resolution spectroscopy, as well as having a smaller volume of systems. And then future potentials for research are materials that can operate at higher temperatures, like perovskites with thallium bromide, or working with Cherenkov time of flight measurements, or working with cheaper fabrication methods such as solution growth. So that concludes what I got today. If you have any questions, please go ahead and ask.
Thanks so much for your talk, Eric. I learned a fair amount today. We have a couple questions in the chat. One is from very early on, which I think I'll go to second. The first question that I want to ask is from Stephen Alexander Bryant with Excelsior University. He comments, since I worked in an R&D lab with ceramics that mainly focus on oxide formed crystal formation, silicon oxide have multiple phase transformations, which can cause the crystal to change when energy is imparted on it. Could your crystal be going through a phase change over time, causing the divergence of your peak energy?
Short answer, yes, it's possible. We mainly focus on the readout of the signals and the associated electronics with that. So unfortunately we're not materials experts in this group. So what you're presenting could entirely be possible, as far as I know.
Sounds like a future collaboration. The other question was from very early on when you were talking about the material properties. Umar comments, the higher the electron mobility, the better the detector. And from your table, HPG has the highest electron mobility. Why is it that thallium bromide is considered the best in this respect, or in your opinion?
No, if I implied that thallium bromide was the best, that was my mistake. I was trying to say that that germanium is definitely the best in that respect, but thallium bromide is still usable, just knowing, as long as you know what those characteristics are.
Fair enough. Thanks, Eric. if anyone else has questions, please feel free. We have some time left in our lecture. You can drop them in the Q&A, or you can just raise your hand. Happy to unmute a few people. Yeah, we have a lot of extra time, or else we'll just be ending our lecture early. So please, if there are any questions in the audience. In the meantime, I'll try and come up with a good one. All right, so, oh, go ahead, sorry. I was gonna just ask one question. I may have missed it earlier in your lecture, but you were showing the divergence in your waveform over time. Did you provide more commentary on why that divergence might be occurring, or have you been investigating that more closely, or have you just been using new equipment to that doesn't show this feature?
So we're still researching why it's happening, but so maybe this isn't the best one to show. So this difference here, it implies that the center is not changing over time while the edge of the pixel is. And then based on the shape of the waveform here, it kind of implies that one of the things about semiconductors is that electrons, as the cloud is traveling, electrons are getting trapped in the crystal structure and then also getting detrapped from the crystal structure and continuing to move. So the shape of this waveform, that since it's rising a little bit faster and a little bit higher than the center events, kind of implies that there's something going on the edge of the pixel that's detrapping more electrons as the cloud is traveling towards the anode.
Got it, thank you. We have some questions that have popped up in the meantime, so still plenty to go through. Start off with an easy one. Sorry if you explained already. Why do you operate HPG at a low temperature?
Sure, yeah, I can go over that one. So here it's because of the band gap. So this small band gap means that not a smaller amount of energy is required for a valence electron in germanium to jump up to the conduction band and conduct. So at room temperature, it's very easy for these electrons to jump between the bands, and that movement will create noise as you're trying to read out, and will essentially mask the signal of any radiation events that are occurring in the crystal. So that's
thanks, Eric.
Okay, yeah.
Oh, sorry. Yeah, no, I think that was a good answer. Oh, got a few other ones coming up. From William, I heard mention of thallium bromide being investigated as a possible room temperature semiconductor. I was under the impression that room temperature semiconductors were considered impossible, like cold fusion. Am I mistaken, or has room temperature come to mean something different in the field?
A room temperature semiconductor.
Right, because you are operating at room temperature, correct?
Yeah.
So I think you've shown the proof, but can you maybe clarify why William might be confused?
Yeah, I think this is probably more foundational science from like decades before me, but I mean, there's lots of materials that are used, lots of materials used as room temperature semiconductors. I mean, we attend a conference every year at IEEE that's specifically devoted to semiconductors that operate at room temperature. So it's definitely possible.
Okay, we have another one from Siddharth. I'll do a little proofreading before the next one. Sorry about that, William. Siddharth asks, it sounded like tellurium bromide is better than CTT. Is that true? If so, why? With a lower band gap, CTT not produce more charge pairs, therefore possessing better statistics?
Okay. So yeah, theoretically, thallium bromide should be a better radiation detector than CZT. Just in practice, we haven't found that yet because things like it changes over time. I mean, changing over time is a big problem that we're trying to overcome right now. If we can get thallium bromide to be stable for a long period of time, that would be really helpful. I know before me, a lot of crystals were made with pure thallium bromide. So those crystals would they would provide really good spectroscopic resolution, like easily to 1% at 662 keV. But they suffered from this problem of polarization where you would see the photo peak on the first day when you operated at room temperature, and then in maybe a couple of days or even a few hours later, that the photo peak is gone. The signals just have a very inconsistent amplitude. I think back then they found that operating it at just -20 Celsius, so definitely not room temperature, but not like cryogenic cooling like you need for germanium, helped with the longevity of the crystal. But that temperature is also low enough that it would make it difficult to commercialize. So I know different formulations are being tried to try and to get thallium bromide to last longer at room temperature. And I think the crystals that I've been working with as a graduate student have shown pretty good longevity. But again, even with some time, we're still seeing some problems. Yeah, I think that answered part of the question. Also, the lower band gap. So the question was about band gap and charge pairs. I think might be conflating to the band gap has to do with preventing thermally excited electrons from jumping from valence to conduction, whereas the ionization energy is the pairs created from the interaction of ionizing radiation. I guess to explain there, the reason that germanium is better is because it takes less energy to form a pair. I guess for the same energy, germanium will form far more pairs, far more electron hole pairs, which can be measured and help reduce any problems that might be created that might introduce noise or uncertainty to the measurement. I hope that answers the question.
Thanks, Eric. And to clarify earlier, I misread William's question. He was asking about superconductors and not semiconductors. So room temperature superconductors, in fact, I believe do not exist. So to go back to William's question, we were talking about semiconductors today, not room temperature superconductors. But I'm sure that would be a fun chat for another time.
Yeah, it's well outside of our research here.
I think we have another quick one just on the HPG. So a higher temperature would make HPG malfunction, as a question. 77 Kelvin is a pretty low temperature. How is it kept at that temperature?
So the two methods that I've seen are either with liquid nitrogen. So you have a detection system, and then you have this big clay, or I think it's clay. I'm not sure, actually not sure the material they're made out of, but this big jar called a dewar that's just full of liquid nitrogen, and that's cooling the germanium. Or there are some commercial germanium systems that use mechanical cooling. So it's just a battery and like a Peltier cooler to try and keep the crystal cold. Yeah, but it takes a lot of weight. It adds a lot of weight because you need a lot of battery power to cool this. And then I've heard that they break somewhat easily. So I can't confirm that myself. I haven't used those, but it makes it hard to use in the field. It makes germanium much more of like a lab system than like a field system.
Yeah, and to expand on that, we actually have a mechanically cooled HPG in our lab. I think with nitrogen cooled, you can get slightly better energy resolution because you can get even a little bit colder. But yeah, it is still a pretty bulky detector to take around.
Yeah.
So yeah, thanks for that answer, Eric. The last one, and I think we'll go ahead and adjourn. It's from Patrick Gunden. Has a handheld field work been tested using the tellurium bromide semiconductor, and how has it performed with temperatures higher than room temperature?
Okay, so I think there's a company called CapeSim, and I believe they attempted to commercialize a thallium bromide detector. I'm not sure how successful they were on that, though. That's the only commercial attempt that I'm aware of. As far as I know, thallium bromide is still a lab system. The project that I'm working on has been transferred from us to or it's actually going to be a new solicitation by the government for the project. But yeah, it's still a research or a lab-based system. I don't think anyone has really made a successful operational thallium bromide yet. And then as far as performing at temperatures higher than room temperature, we're working on that right now. We've done some testing up to 40 degrees Celsius in an environmental chamber. We're still able to discern photo peaks at that higher temperature, but the resolution has gotten much worse, and then measured energy from events has also decreased. So that's another problem that we're researching right now.
Got it. Thank you. And we just had one more pop up. Abhishek is asking, there may be more semiconductor materials other than these three we covered. What is the most efficient until now for gamma detection?
Oh yeah, I forgot to mention. There's I only talked about 3, 4, 5 materials in this presentation. But there's a lot of different semiconductors out there. Other than CZT, there's CAD tellurium, silicon. I think there's a couple out there using gallium or lithium for like neutron detection. So yeah, there's a lot out there. These are just the ones that I have the most experience with. As far as efficiency for gamma ray detection, that is a good question. I know we've done some efficiency studies in our group with CZT. I think we're seeing something on the order of like 50% efficiency, but don't quote me on that. Yeah, the shorter answer is I'm sorry, I can't really tell you which one's the most efficient. Yeah, sorry.
No worries, Eric. I think just a quick estimate off of what you're showing here per volume. It looks like the tellurium bromide has the highest effective Z, so that would probably be the most efficient. Correct?
I mean, probably that makes sense.
Yeah.
I haven't measured efficiency myself, but yeah.
Fair enough. Thank you. And then Siddharth, I saw your last question in chat. I'm just going to go ahead and do a written answer. But thank you all so much for attending, Eric. We greatly enjoyed your answering all these questions and providing your expertise and your lecture today. The recording will be up online as soon as we're able to get it up by the end of the week for sure. But yeah, hope you all attend our summer school next week. We'll be back on next week, Tuesday, and we'll be starting our neutron week, talking about neutron physics. Thanks again, Eric.
All right, thank you.